Yeah, so do you have a plan for this problem, for the first one, 8.1? We need to get the values of a, b, and c in that equation, and this is all the information we are given. So normally, when we are required to work out the values of two unknowns, normally it's wise to to try by all means to come up with two equations that involve the two unknowns. Now we can apply the same principle when dealing with three unknowns. So if we can get three equations that involve the three unknowns, there might be a way forward. Do you have an angle or an approach that you wanna try?
Um, I'll be back because there's someone at the door.
Okay. So let's look at the information we are given sentence by sentence and see what we can draw from it or from them. So first, we are given the equation of f. What we can observe is that f doesn't have an x squared term. Can you see? Yeah, that's what we can pick up from by looking at the equation. Now we are told that f has a turning point at D. Now f has a turning point at D can be translated in a number of ways. I think at least two. D is a point on F. Now that means that the coordinates of D must satisfy the equation of F. So remember, I was saying that we are required to work out the values of three unknowns. Now, if we can get three equations involving the three unknowns, then there might be a way forward for us. Now, D is a point on F. That means the coordinates of D must satisfy the equation of F. So we can therefore conclude that 32 must be equal to, or 32 is equal to F at minus 2. Can you, does this step make sense?
Yes.
Okay, now what we can do is we can plug in this value of x into the expression of f. Then we will have one equation. So we have a into minus 2 to the power 3 plus b into minus 2 plus c. Now let's simplify this equation. If we were to simplify it, what would it simplify to? Mm, can you please help me simplify this equation?
It's minus 8a plus minus 8a minus 2b. plus C.
Okay, thank you. This is one equation now. We are told that D is the turning point of F. That means D is a point where the tangent to F is horizontal. The tangent to F at D is horizontal, and also the tangent to F at the other turning point is also horizontal. So that means F prime at D must be equal to 0 because D is the turning point.
Yes.
Yes, so D is a turning point. Therefore, F prime at the x coordinate of D must be equal to 0. But now what is F prime? F prime in this case in terms of x will be what? If that is F.
It's 3ax squared
Yes,
plus B.
plus B. This is F prime now. The x coordinate of D is -2. So this means F prime at -2 is equal to 0. But what is F prime at my x equals to -2? We can come up with the expression using that equation. We're gonna have 3a into -2 squared plus b equals 0. Now, what does this one simplify to?
Negative 12a plus B.
Negative 12a. Notice that, notice that we have a negative inside and an even power. So remember that if we have a negative base, or if a is positive, then minus a, any negative number to the power n, will be equal to positive a to the n if n is even, and negative a to the n if n is odd. So this means here the 4 is gonna be positive. So we're gonna have positive 12a plus b equals 0. We have a second equation. Now let's look at the information, or the other piece of information that we are given. We are told that the gradient of the tangent to f at x equals 3 is 15. So remember, f prime represents the gradient of the tangents to f as we move along x, or as we move along the x-axis. Now, when x is equal to 3, the derivative is equal to 15. So this is just to say, this last sentence, the gradient of f at x equals to 3 is 15. We can translate this as f prime of 3 is equal to 15. Okay, so we're gonna find our third equation here. Since f prime of 3 equal to 15, we have this. we can again use that expression for f prime. Then we're gonna have 3a into 3 squared plus b equals 15. Now let's simplify this one. What will this one simplify to?
It's 27a plus b.
Yes, 27a plus b equals 15. Now we have three equations, one there, one here, and another one here. Notice something about the last two equations. They both involve two identical unknowns. So we can solve these two first and then use that one to get the value of c. We can solve for a and b using these two and then use that equation to solve for the value of c. Now let's say this one is 1. Let's say this equation is equation 1, and let's say this one is equation 2. Now we can make a variable the subject from any one of these. So which variable do you want to make the subject?
B.
B. In which equation?
The first equation.
Okay.
Or the second one.
Or the second one. Thank you, because I was becoming stressed of the issue of space. So if we make B the subject here, B will be equal to 15 minus 27a, isn't it? Now let's call this one equation 1 and let's call this one equation 2. Now we're gonna sub 1 into 2. Then we're gonna get the following. Equation 2 is 12a plus b, but b is just 15 minus 27a. So because the sign in front of b is positive, we can just not write the brackets, but had it been negative, it would have been essential. So we have equals 0 there. Now let's solve for a. What step can we take?
You take 15 over to the left, to the right hand.
Then it's minus. Then what are we left?
Then you simplify it.
Yes.
We'll be left with negative 15a.
Negative 15a. Yeah, then we have this. Then we can divide both sides by minus 15. Then we have positive 1. So that was the target. Now we can just use this expression to get the value of b. And therefore say b will be equal to 15 minus 27 into 1. Now what will be the value of b?
It's minus 12.
It's x minus 12. So now let's go back to that equation. Let's call this one equation 3. There. Now we're gonna bring back equation 3 and then plug in the values for a and b. What was this procedure? Did it make sense, the whole procedure up to this point?
Yes.
Okay, yeah, the goal was just to come up with 3 equations, so this seemed to be the way to go. Now here we can say from equation 3 we have the following. We have 32 equals minus 8 into a. A is 1. And then we have minus 2b. What's the value of b? Minus 12. Now plus c. Then we can just solve for c. So what will c simplify to? First term here we have minus 8 there. And then second term we have plus 24. Then plus c. Minus 8 plus 24 gives us 16 plus c 32. That means c equals 32 minus 16, just 16.
16.
Yeah, this is what they had. So in fact, I think we should leave it there. And then okay, so yeah, we put those values. Now, this was 6 marks. So now we are required to calculate the coordinates of the point of inflection. Now, how can we do that? The x coordinate of the point of inflection.
We look for the second derivative
Well,
of it.
yes, so look for the second derivative and then do what?
You substitute it. With the answer, you substitute it back into the equation of it.
Okay, but yeah, that's if we needed the y coordinate of the point of inflection, we're gonna substitute the x value into f. Yeah, but they only want the y coordinate. So yeah, we need the first derivative. Now let's write the equation of f in a nicer way, since we have the values of a, b, and c. F of x is equal to x to the 3 minus 12x plus c plus 16. This is f. Now we need the second derivative. Okay, but we already have had the first derivative there. But yeah, Okay, but we had the first derivative in terms of a and b. So now let's work it out explicitly.
It's 3x squared
3x squared
plus 12.
plus 12 minus. This is f prime. Now what is f prime prime? Do people even call it that? Second derivative 6x only there. Okay. Now to get the point of inflection, the point of inflection is where the second derivative equals 0 there. By the way, how do you define an inflection point? What is an inflection point in words? Not the procedure how to find it.
Point of inflection is the point where the curve, I'm not sure now.
Yes.
The point where the curve changes, I think.
Changes something. Changes what?
Changes shape.
Yes, changes shape. But shape in what regard? In terms of concavity. Yeah. Yes, it goes from, or this graph goes from concave down to concave up after or at the inflection point. Yeah, so okay, we need to solve this equation to get the x-coordinate of this point of inflection. So we therefore solve 6x equals 0. Is that so?
Yes.
Then x will be equal to 0. Okay, I think I did this question incorrectly with someone. That's why I stopped for a bit. Yeah, the point of inflection is 0. Okay, so that means the y-intercept is the point of inflection. That is the point of inflection. But remember, these graphs are not always drawn to scale, but it seems drawn to scale, this one. Okay, now, okay, this is the x coordinate of the point of inflection. We are done with 2.1. Now 8.2.2 requires us to determine or to calculate the values of x for which f is concave down. Now f is concave down for which values of x? Remember, that's the point of inflection and its x coordinate is 0. So for which values of x will f or is f concave down? Before the inflection point or after the inflection point? Before, ne? So it's before, all the way from minus infinity up to the point of inflection. but now we are going to focus on the x coordinate of the point of inflection. So it's going to be when x is, we can write this in interval notation or in inequality notation. We can say when x is less than 0, or we can say when x is an element of numbers from minus infinity up to 0. We are not going to include 0 because at 0 x is neither concave up or down, or it could be either concave up or down. Yeah, but do you understand this reasoning?
Yes.
Okay. Now 8.3. They want to know the coordinates of d dash, or d that thing, the image of d when f is reflected about the x-axis. So if we reflect f about the x-axis, every point, or what will happen to every point on f if we are reflecting f about the x-axis?
Will be opposite. It will have the opposite.
That's vague. What will be opposite? The opposite of what? Okay, maybe things become complicated when you look at the big picture. Now let's look at only the point D. What will be the coordinates of D if we reflect D about the x-axis?
Oh, the y-axis. The y coordinate will change.
Yes, all the y coordinate will change. So now, what will be the new coordinate of D? Or D
Okay, minus 2 and minus 32.
Yeah, well done. So now, if we were to look at the big picture, if we are not just, or if we reflect the point only, the point will be somewhere there, minus 2, 32. But now if we look at the entire graph, it will sort of look like that. Yeah, then it will look like this. Now, if this pink curve is a reflection of f, how can we write it in terms of f, since it represents all the points of, or all the points of f reflected about the y-axis? We can call the pink curve minus f there. Yes, because all the f values, or in other words, all the y values, change sign to negative. Now, 8.4 is f a function. Do you know how to test whether a graph is a function or not? Or whether a graph represents a function or not? Okay, I figured you might not have done that already. So, but now, this is in the section of functions and inverses, but don't be alarmed. or if a function is not a function, then it's just a relation. Ne? A relation, a relation between x and y. Graphs, or the graphs that we work with, are relations between x and y, ne? Because they indicate sets of coordinates, or they represent sets of coordinates. Now, this relation is defined by a rule. The rule which we call an equation. Ne? That's why functions have equation. That those equations represent the rule that the function or that the relation follows. If a function is equal to x squared, the rule is that we square every input value. Ne? So now some functions or some relations are not functions, like what you are gonna work with this year, the circle. We are gonna work with the circle on the Cartesian plane. Ne? And then the equation of a circle is given by x minus a plus y minus b squared equals r squared. Where a and b are the center, where or the point a and b is the center of the circle. So, and r is the radius. So we are going to work with functions of this kind, but these functions, or they are not functions, rather they are relations. So an example of a circle on the Cartesian plane would look something like that. A and B is the center. So now how do we test some relations are functions and some are not? No. Some are functions and some are not. So we can classify which relations are functions and which relations are not functions. Now, for a relation to be a function, the relation must pass the vertical line test. So if a relation passes the vertical line test, then the relation is a function. But if it fails the vertical line test, then the relation is not a function. Now, how do you pass this test? You pass this test like if a vertical line passes, if any vertical line on the plane touches F only once, then it's a pass. No. So some functions fail this test. Now, examples of those that fail this test will be the circle, because if we draw a vertical line anywhere, this line will touch the graph twice. Can you see?
Yes.
Okay, but if if we make it a tangent, then it will touch it only once. But every other vertical line passing through the graph will touch the graph twice. So the circle is not a function, it's just a relation. Now let's look at the functions that we deal with and why they qualify as functions. Why am I doing this to myself? Let's consider a parabola. A parabola can be concave up or concave down, but regardless, it will always pass the vertical line test. Can you see? Regardless where we position the graph, it will touch a curve only at one point. Similarly for the concave down parabola. Now, other functions that we work with, the exponential function, or the one that we are going to work with, the logarithmic function. Okay, but even the hyperbola will also pass the vertical line test. So the hyperbola qualifies as a function. Similarly for the straight line, straight line will also pass. But now, even the trig functions will pass this test because the sine function and the cos function are they sort of go like that. So such graphs also pass the vertical line test, but the circle is the most notable one that we are going to work with in metric. So this is an example of a function that's not a function. Now, in this case, we are asked if f is a function. Now, you are permitted to use the vertical line test in your exams. My student was, or my other student was skeptical when I told him that, but I showed him in the memo that f in this case, or what can you say about f? Is f a function?
Yeah.
It is. Why is it a function?
Because it touches the vertical line once.
Yeah, or you can just say it passes the vertical line test. Yes, f is a function. Passes the vertical line test. Now, this is informal. This is an informal way of defining a function or of testing a function. Now, let's try to be more formal to understand it in a more formal way. What is meant, or how can we decide that a function is a function or not? I'm gonna miss this comma. It's useful. Okay, let me bring this closer and say that more formally. A relation is a function if it assigns one y value to every x value or a relation f ish, it's bad. A relation f is a function if it assigns one y value to every x value in the domain of f. Now, please process this statement fully in the domain of f. We say a relation is a function if every x value in the domain of f has only one y value. Now, when it comes to the circle, some x values correspond with two y values. Can you see? That's the reason why it fails the vertical line test. Notice that this particular x value, let's say x, will have two y values that correspond with it on the function. Can you see? Yes, that's why it does not match the description, or there are some values in the domain of f that have two y values or that correspond with y values, or that have more than one y value assigned to them. But with all the other functions, like these ones, if we look at the purple one alone, then we can see that every x value in the domain of f is assigned one y value. There is no x value in the domain of f that has two y values. Now, there's another classification of functions. After a function passes the vertical line test, it must now pass another test. That test determines whether the function has an inverse or not. Has an inverse function or not. So some functions have inverse functions and others do not. But we are going to talk to that a little later in the course, not now. So how has it been in class with the work?
It's a lot.
It's a lot. And it's about to get even more real. Your maths term 2, term 3 is hectic. But
That's what my teacher.
you're not. Okay, I didn't hear you clearly. Sorry about that.
See, that's what my teacher says.
Yeah, it's the truth. But yeah, keep working. We'll be fine. Now, okay, I wanted us to draw a graph ourselves. So before we get to that question, I want us to do this one first. Sorry for only remembering now. Now, in this case, we are not given a sketch. So, okay, information we are given is the equation of f, but it's written in that form. And then we are told that f prime at 1 is equal to f prime at 3, and they are both equal to 0. F prime at 1 equals f prime at 3, both equal 0. Then we are further told that f, the original, at 1 equals 4. Now, 8.1 requires us to show that f has a point of inflection at x equals 2. Again, how can we prove this? How can we prove that the x coordinate of the point of inflection is 2?
Find the second derivative.
Second derivative, yes. But now f is written in an unusual form. F is written like that, so it's not easy to differentiate it right away. Yeah, so let's write it in standard form. It's factorized. That means should we need the x-intercept in the future, we can come back to this stage because it's already factorized. But now in standard form, how can we write f of x? We can first deal with the brackets since they have an exponent 2 and leave this x outside for a while. Then what will we have inside the brackets?
It's x squared minus 6 plus 9.
X squared minus 6x plus 9, very good. Then we can go further and say that we distribute this x inside. Then we're gonna have x to the 3 minus 6x squared plus 9x. This is f of x. Now we can differentiate what will be f prime of x. Oops. And Donna, can you please excuse me for a minute? Okay, I wanted to pause derivative already. Okay, thank you. What's the first derivative?
It's 3x squared
3x squared
minus 12x plus 9.
plus 9. Then f prime prime.
6 minus 12.
6x minus 12. Now, to get the point of inflection, just to label for them point of inflection. We are solving f prime prime equals 0. Now we are solving 6x minus 12 equals 0. What will be x?
2.
X will be positive 12 over 6. 2. So yeah, we are done with 8.1. Let's check out 8.2. 8.2, they want the sketch. Yeah, but already they want the sketch of f. Now we must show the intercepts, x and y intercepts, all of them, and the turning points. So what are the turning points in this case? Remember to get it. Yes.
X intercepts when you solve for first prime f prime x
Equals 0. but they already did the dirty work for us. They have determined that f, or they are told, they've told us f prime at 1. Like, we don't need to solve for x anymore. If we were to solve for x here in this f prime, we can expect to get 3 and 1, or 3 and 1 from these two. Can you understand that? Or you want us to go through the process?
You see what you said again.
Okay, yeah. Since f prime of 1 equals to f prime of 3, that is equal to 3 to 0. That means, or we can therefore say, x coordinate of the turning point equal to 1 or can therefore say x equals to 1 and x equals 3 are x coordinates of the turning points. So now we need the y coordinates of the turning points so we can locate the points in full. Now, to get the y coordinates, we must plug in these values of x, of the x values of the turning points, into the equation of f. Now we must evaluate f at 1. What will be f at 1 if that is f? F at 1 will be 1 to the 3. Can you please help me with your calculus? In fact, here's something I thought of. We might find it easier to just plug in into f the way it was written, given to us. Here you're gonna substitute only twice, and here we gotta substitute 3 times. So if you find it more efficient to use the first one, you are welcome to do so.
It's 4.
F at 1 is 4. And what about f at 3?
It's 0.
It's 0.
Yeah.
Okay. So now we have the turning points. We have the turning points. Now we need the intercepts. How can we get the y-intercept? The y-intercept is f at 0, when x equals 0. So what is the value of y when f is equal to 0?
It's 9.
I don't think so. Did you plug in f prime or f? It must be 0.
It's 0.
Yeah.
I was like,
You used f prime.
that's what I was looking at.
Oh, Okay, but there's something that I forgot to summarize there. The turning points. So one turning point has which coordinates? What are the coordinates of the two turning points?
It's 1 and 4.
1 and 4.
Yes. And 3 and 0.
3 and 0. Thank you. So now the y-intercept is 0. The origin, 0 and 0. Now what about the x-intercepts? To get the x-intercepts, yes,
it's 0 and positive 3.
x equal to 0 and x equals positive 3, because remember, using f in that simplified form, it's already factorized. No, the factorized form, not simplified. Using this, you can just jump to these steps. Very good. Now, do they want to know the point of inflection? Do they want to see it? They didn't mention it, the point of inflection. Intercepts, turning point, no point of inflection, but normally it's a key point of the graph. So, but anyway, let's not try to be clever. We have intercepts or x-intercepts at the origin and at x equals 3. Also have a point there. Now, the origin is both the x-intercept and the y-intercept. Now, other key points are 1 and 4 and 3 and 0. So this point is also a turning point, 3 and 0. And then we have 1 and 4. So if 1 is here, then sort of have a turning point there at 1 and 4. So if you've indicated a point with a dot on the x-axis, I think you don't need to write out the coordinates, but please confirm with your teacher.
Okay.
Yes. So yeah, but normally I don't think it's necessary to write out the points, but just to be safe, please confirm with your teacher. So now, cubic functions can either start off as increasing or start off as decreasing. Now, they start off as increasing if A is positive, then they start from bottom going up. But now, if A is negative, okay, but I'm not happy with the way I do this function. It might be something like that, or it can also be when the graph doesn't have a turning point, but it will still have a point of inflection. So, but now if A is negative, then the graph starts off as decreasing. Then it might take this shape if it has turning points, and it might look like this if it doesn't have turning points. But yeah, this is if A is negative. So in our case, or for question 8, is f, or the value of a in f, positive or negative?
It's positive.
It's positive. So that means our graph will start off how?
Concave down to concave up.
Yes, concave down to concave up. You're using the big words. Yeah, I was gonna say from from bottom going up. Yeah. And then this point, remember, it's also the turning point. Yeah. So
Mm.
f will look kinda like that. Now they didn't mention the point of inflection, but normally it's a key point. So if we needed the y coordinate of the turning point, or the point of inflection rather, did I say turning point previously? I wanted to say point of inflection. In any case, had we wanted the y coordinate of the point of inflection, we were gonna plug in this value into f, the original, yeah, to get the corresponding point, or the y value of the corresponding point. Yo, now 8.3. Yo, I think we need a copy now. Yo, for 8.3, they wanna know for which values of x will y equals negative f of x be concave down. Ish. I wanna ask you something, but I don't know how to phrase the question. How can you describe negative f of x in relation to f of x? Hello.
If it if of fx has been reflected
Oh,
uh, reflected on the x-axis.
very good. Y is a reflection of f about the x-axis. That's an important point to note. Now, had we been okay, we can just as we can use the sketch of f to determine the values of x where f is concave down. We can also use the same graph, or the graph of y, to determine the values of x for which y will be concave down. Now, f is concave down where? From where to where?
From 0 to 3.
From 0 to 3. Not quite, because remember where the point of inflection is. I think it's where x equals 2. Né? So
Yeah.
the point of inflection is somewhere there. Now, before 3, f has already changed concavity. Now, try to think about it again. The values of x for which f itself is concave down. like it's concave down everywhere before the point of inflection, and it's concave up everywhere after the point of inflection. Ne? So remember that what is the domain of F? For which values of x is F defined? Is there anywhere? Yes,
0 and 3.
0 and 3. Okay, so when you say the domain of F are the values from 0 to 3, you are saying that everywhere else F is not defined. And is that the case? This set is part of the domain, but it's not the entire domain. No. So remember, we consider values from minus infinity up to positive infinity. So from between all these values from minus infinity to positive infinity, are there any values where F is undefined? I don't think there is. Regardless of what x value we input, we will get a real value for F. So for that reason, we say the domain of F is all the real numbers. Now, in this case, I wrote it in set notation. We can write it in interval notation. We can say x is an element of all the numbers from minus infinity to positive infinity. This is the domain of F. Now, from all these numbers, from the domain of F, we must select a set of values for which F is concave down from this set of the domain. So in words, we can say F is concave down before the inflection point everywhere. So using math symbols, or yes, in terms of maths, in math terms, for which values of x is F concave down? F itself first. Or would it help if we draw the reflection on the sketch?
Yes.
Okay, so the reflection, the turning point, this turning point will be a point on the reflection as well. And these x-intercepts will also, both the x-intercepts will be points on the reflection, and then 1 and 4 will become 1 and minus 4 if we reflect about the x-axis. So then the graph of the reflection will look kind of like that. This will be y equals negative F. So I want us to observe a pattern here, that Okay, no, I'm drawing this line at the wrong place. I want to draw it through the inflection point. This line passes through the inflection point. Now, it's not an axis of symmetry. I don't think it is. Okay, but then, yeah, if we look at this line is the line that cuts F and Y at points where they change inflection. By the way, the point of inflection of the reflection will be somewhere there, né, reflecting that point. So notice that everywhere, okay, the question that I was asking first was for which values of x is f concave down. So f is concave down everywhere until the inflection point. Né? So whenever x is less than the inflection point, then f is concave down. Can you see? Like if we were to extend this line on and on, this graph will follow the same pattern indefinitely. Né? So regardless, even if we increase the values of x, this graph will always be defined and concave down. Né? Now, f is concave up where? F is concave up where? My where is not so good, but f is concave up where x is above the point of inflection or beyond the point of inflection. Whenever x is greater than 2, then f is concave up. Né? Now, what about the reflection? The reflection is y. Né? So y is concave down whenever f is concave up, and vice versa. Whenever f is concave up, the reflection of f, y, will be concave down. Does the graph illustrate that clearly? Okay, so it helps to sometimes compare graphs, especially when you are asked about a graph that is related to a graph that is in front of you or that you already have. For example, we had the graph of f. Now we are required to use the graph of f to make predictions regarding the graph of the reflection of f. So yeah, it's important to know how to visualize reflections or all sorts of transformations, as well as the derivatives. Tomorrow we are gonna go a little deeper in the relationship between the graphs of the function and its derivatives. Did you do that in class?
No, not yet.
Okay. But just to complete these notes on the side, we can say y is concave up where? When x is
From
where?
until 2.
Oh, from minus infinity until 2. So whenever x is below 2. By the way, there are different styles now of writing. In the style, we wrote it in inequality notation. So we can write the same statement in interval notation. We could say when x is an element of numbers from minus infinity up to 2 and not including 2. And similarly here, we can write it in interval notation and say from 2 up to positive infinity. Similarly here. Yeah, so let's try to answer the question. For which values of x will y be concave down? If we look at the sketch.
Is the question asking us to look at y equals to negative fx or fx?
Negative fx.
Okay. It's from 2 to negative infinity, 2 to positive infinity.
Yes. 2 to positive infinity. Well done. Let's keep going. More transformations. I'm not really a fan of transformations, but they are very challenging. 8.4.1. Use your graph to answer the following questions. Determine the coordinates of the local maximum of h if h of x is equal to f of x minus 2 plus 3. So f of x or h is a translation. It's a translation of f, but it's a translation that involves 2 steps. Can you describe the transformation of h or the transformation of f to obtain h? Do you think you still remember transformations?
I don't know.
You don't know. Okay, so as a challenge, I'm gonna ask you to do these ones at home on your own. The next two, 8.4.1 and 4.2. Yeah, if you look somewhere in our notes, you will find a way to describe. Remember, I first asked you to describe the transformation. Okay, it's not what the question was asking, but I'm adding on to this. First, describe this transformation, and then after describing the transformation, try to determine the coordinates of a local maximum of h. Now, Mm,
What does local maximum mean?
okay, local means not everywhere. Ne? Not everywhere in the domain, in some parts of the domain. That's a good question, but I wasn't ready for it. But not everywhere in the domain. In other words, in some interval. Eh, in some interval, this is the maximum. So now, when we spoke about quadratic functions have one extreme point. Ne? It's either a maximum or a minimum. Ne? Like if it's concave down, it will have a maximum. I can hear myself. It's unusual. Then if it's concave up, it will have a minimum. So now, when it comes to cubic functions can have up to two turning points. So now, this one was not a local maximum, it was an absolute maximum because it was greater than. Okay, I wanna stop being shy to use formal maths words with you. So now, absolute maximum. Absolute maximum is a y value. Yeah, keep that in mind. It's a y value. So we say a value is an absolute maximum. Let's say f of a is an absolute maximum if f of a is greater than or equal to f of x for all x in the domain. For all x in the domain. Some domains are not the entire real number, so I'm just gonna say in the domain of f. Again, just to test you, how do you define domain? What is a domain of a function? A domain is the values of x for which f is defined. For which f is defined. Now, if for every x in the domain of f, f of a is greater than f of x, then f of a is the absolute maximum. Now, sometimes they don't use local maximum, they say relative maximum. So, the local or relative maximum. eh, Relative maximum, we will say f of a, or local maximum is f of a if f of a is greater than f of x, all f of x, or over some interval. Yo, sekgowa over some interval in the domain of f. So, for example, let's look at this rough sketch of the cubic function. Let me move it away. Oh, but now, I'm a bit confused, but I'll make a plan. I always do. So yeah, this one is an example of an absolute maximum. Again, absolute minimum. Now this one will be a relative maximum or local maximum. Why? Because it is greater than many values of f, but not all of them. Over this interval, let's say we have the Cartesian plane there. Now, this one is only a maximum for these values of x. It's only a maximum for this part of the domain, which we sometimes call an interval, only for a part of the domain. But for this other part, this value is not a maximum. Can you see? Yes. So hence we call it local or relative maximum, because it's a maximum only in South Africa, but in the rest of Africa, it's average. So yeah, the same comparison can be made with regard to the minimum values. Yeah, so now remember the maximum and the minimum. As a collective, we call them extreme points. As a collective are called extrema. Or let me call them first extreme points. Now, when they are in singular form, we call them extremum. But now in plural, we call them extrema. So sometimes you can be asked to show all the extrema of the graph. Extremum, but they are both extreme points. Okay, yeah, remember 4.1, 4.2 is homework or part of the homework. Okay, but you won't have a lot of time, but so let me not give you too much work. Now, is it time up?
Not yet.
Oh, not yet. Yeah, there's still enough time. We can make some progress in this section. Now, For this one,
So
yes,
can you go back to the previous question quick?
yes. Here,
Yes. Is 8.4.1.
yes.
Can we solve it by? Is it fine if you say same sign, change sign to get the points?
To describe the transformation,
Yes.
it's not accurate. It's not an accurate description.
Okay.
Mm, a clue I can give you is that there are two, or this type of transformation is a translation, ne? And then there are two transformations in total. Here, it's moved one way and it's moved another way, all at the same time.
Yeah.
Yeah. Okay, so let's look at this one. Is everything clear on the screen?
Yes.
Okay, so we are told that f has that equation. We are given the equation in full. Okay, the graph of f is shown, and a and b are the turning points. They are the extrema, the relative extrema, because it's a cubic function, they are not absolute. So now A and B are turning points, and then C is the y-intercept. D, E, and F are the x-intercepts. This is all we are told. That's the graph. Now they want us to write down the coordinates of C. It's 1 mark, so maybe the answer is right in front of us.
It's 0 and 9.
0 and 9. Now 8.2. How do we determine the intercepts? Because we are told that D, E, and F are x-intercepts.
We solve x.
We solve x where? That's 2, but where? Where do we solve for x? In which equation?
Of fx.
Of fx equals 0.
Yes.
So we must solve for x in this equation. Equals 0. Now, what's the first thing we do? Hello.
Hello.
Okay, are you working it out?
So for this I normally use synthetic division.
Yes,
Because
not a problem.
you first find the common factor.
The what?
The factor
Mm,
of the equation. Yes.
yes. So which factor did you find?
I haven't found one.
You haven't found one, or you haven't started yet.
Yes.
Okay, so which values? Remember, to find a factor, we must first try out a value that's gonna satisfy the equation, the root of the equation. So we're gonna try multiples of 9. 1 and minus 1, 3 and minus 3, 6 and minus 6, 9 and minus 9. Not those, just these. So, okay, let's try them both sides. Which ones do you want to take, the positive or negative?
Negative.
Okay, then let's see, let's find the factor. Okay, I found one. I think so, but just to verify, did I enter everything correctly? It seems so. So 1 is a root. So that means what is a factor?
Mm. X1.
X minus 1. You want to know that echo is disturbing. So we're just showing that f at 1 equals 0. Therefore, x minus 1 is a factor of f. Okay, so we can set up the synthetic division box. Okay, that echo, it's really bad. Did you try to stop it? Or you don't know what's up? What's causing it?
I think it's connection, internet connection.
Okay. So, okay, remember outside we don't enter minus 1. We enter the root as it is. 1. And then the coefficients of f. These. Then what are the steps?
You bring down
Bring down 2.
option 2.
Mm,
Then multiply it by 1.
Right, this one. Yeah.
Mm.
And then
Then you add.
yeah, it's gonna be 3. Then 3 times 1 gives us 3. When we add these, what do we get?
-9.
-9. Then -9 times 1 is just -9. Then when we add these, we get a 0. It makes sense because x minus 1 is a factor. So now this therefore means that f of x can be written as x minus 1 into 2x squared plus 3x minus 9. So now remember we are solving this equation, right? So we can immediately say x minus 1 equals 0, or the other factor, the quadratic factor, 2x squared plus 3x minus 9 equals 0. So now, can we factorize this equation? Let's check the nature of roots. Or we've already found the factors.
It's gonna be 2x minus 3 and x plus 3.
2x minus 3
Yes.
and x plus 3. Very good. This means x equals what or what? Or minus 3. What or minus 3?
Negative 3 over 2.
Positive, because minus 3.
Oh,
Yeah, positive 3 over 2. So now 3 over 2 is just 1,5. So now, judging by the sketch, how can we order the values of x? Notice that according to the sketch, the x coordinate of d will be the smallest of the 3.
yes.
And the x coordinate of e will be the one in the middle. So the x coordinate of d will be less than the x coordinate of e, and they will all be less than the x coordinate of f. So the greatest one out of this group is the value of f, and the smallest one is the value of d, and so on. So what's the x coordinate of d?
Negative 3.
Thank you. And the x coordinate of e,
It's 1,
1,5. Yeah, we can write it anyhow. And then x coordinate of f will be the remaining one. 1. Okay, but
so
yes,
isn't 1,5 bigger than 1?
it is. Yes, thank you. I always think small when I see fractions. Then 0.5 there. Thank you. Okay, it's not, they aren't strict on this, but I want you to be careful when they say coordinates. Please list them that way, in point form, in coordinate form. But sometimes they might be specific and say the x coordinates of such and such. So now, because they want coordinates, I think it's safer to write them out in full. The point D is the point 3 and 0. Point E is the point 1 and 0. Point F is the point 1, 5 and 0. But it's a bit silly to write them out in full when they are x-intercepts. But just to be safe. Okay, let's try 8.3. We want the values of x for which f is concave down. How can we approach this one?
I think we first look for the point of inflection.
We need the point of inflection. It's a critical point.
Yes.
So in words, we using just the word or the words point of inflection. How can you describe these values of x for which f is down or concave down? It's the point of inflection. Okay, it could be anywhere, but it looks more like there. But is it before the point of inflection or after the point of inflection?
So
Is f concave down before the point of inflection or after?
it's before.
It's before. So it's from minus infinity up to the point of inflection. Now let's work out the x coordinate of the point of inflection. We're gonna need f. Do we have it anywhere? No, doesn't seem like it. F of x is 2x to the 3 plus x squared minus 12x plus 9. Okay, so we must use f to get the second derivative. But what is the first derivative first?
It's 6x squared plus 2x minus 12.
Minus 12. Now f prime prime.
It's 12x plus 2.
12x plus 2. Very good. Now to get the point of inflection, we solve f prime prime equals 0. So then we're gonna solve 12x plus 2 equals 0. Then what will be the value of x?
Negative 1 6.
Negative 1 over 6. Well done. It's raining this side. Can you hear the sound of the rain?
No.
Okay, I was worried that it might interrupt. Okay, yeah, this is the point of inflection. Now remember what the question was. The question wanted the values of x for which f is concave down. Now we have the coordinates of the x of the point of inflection. Now what can you say regarding the values of x for which the graph is concave down? It's -1/6. It's very close to the origin but not quite there. So yeah, it's somewhere there. These graphs, their scale is off sometimes. So again, is the graph concave down before the inflection point or after? Before. So now, since the inflection point is where x is -1/6, what are the values of x for which f is concave down?
It's negative infinity to -1/6.
Yeah, you're gonna do well at the test stage. I hope so. Therefore, f is concave down. Where x is numbers from -infinity up to -1/6, or we can write this in inequality notation and just say x is less than 1/6. So this one, 8.4, I'm leaving it for you as homework. I want us to stop here because to explain this one, I want to explain it in general terms for all functions before taking on this particular question, or I want to use this question as an example to explain a very important concept that relates the function to its derivative. Are you fine?
Yes.
Okay, can we please start tomorrow? Or meet again tomorrow? I have a request. Hello.
No.
Yes, I want to know if it would be possible to start at 11, or will it be too early? 11 until 1.
You're fine.
Okay, thank you. And
Okay.
yeah, so next time, the other Saturdays, if we work on Saturdays, we'll work at 12. Thank you.